Hello everyone. Now I'm going to walk you through one of the example scenarios which uses PyMarlin. We will use the CFAR data to build an image classifier. This tutorial is based on an official PyTorch blog which also trains an image classifier using CFAR data. We'll start with installing PyMarlin. I've already installed PyMarlin. Now we will import the dependencies and move ahead with implementing some of the interfaces. The most important component in any deep learning scenario is the data. We have separated the data pre-processing part with the model training part in PyMarlin. So the step one will involve downloading the data, pre-processing the data, analyzing it, and creating a final PyTorch dataset. In PyMarlin, data interface and data processor is where you implement your code related to all the steps mentioned above. We'll start with implementing a data preprocessor, which downloads the data and normalizes the data. After that, it displays some analysis result on the data and shows some sample images and their labels. Here it has pre-processed the data and downloaded it. The training data size is 50,000 and the validation data contains 10,000 examples. Here I'm using the test dataset as validation and train dataset for training. Here are some of the examples and the corresponding labels for those examples. Now that we have pre-processed the data and analyzed the data, we will go ahead and implement an interface called data interface, which the model training interface, which is the module interface, uses to create data loaders. This interface is pretty simple. It just needs to implement get train dataset and get validation dataset. Now that our data interface is ready, we'll go ahead and write our training code. So in training code, we'll override PyMarlin's module interface and create a training recipe. But before that, we have to create the model architecture. Here I am creating a two-layer neural network with a nonlinear ReLU transformation in between. After a model network is ready, we will go ahead and implement the module interface. Module interface contains instructions to create data loader, defines the training step, optimizer, scheduler, and the evaluation code. You can refer to PyMarlin's docstring to know more about all these interfaces. To explain briefly what module interface does is it implements these abstract functions. First, it initializes the model network, the loss function, the optimizer, and the scheduler. And then it implements these two functions too, which returns data loaders. And then it also implements the training step, which does a forward pass on the data using the model architecture, and a validation step, which also does the forward pass and records the output for evaluation. After each validation epoch, the outputs from valid step will be used to calculate the model accuracy. Okay, now let's create a module interface. So after we have created the module interface, PyMarlin will do the heavy lifting of training this model. The major components in PyMarlin which train the model are trainer, and trainer backend. So trainer will act as an orchestrator which uses the model interfaces implementation and passes it to the trainer backend. There can be multiple trainer backends, and PyMarlin currently supports a bunch of them. Here I'm using the single process trainer backend. After creating the trainer and calling the train method in the trainer, the model starts training. Here I have limited the model training to maximum 100 training steps and maximum 10 validation steps per epoch. This is done just to ensure that the entire loop and the entire code works as expected. As you can see, the code is working as expected. And now let's go ahead and train the model with the full data. I have already done the training. So the model is trained to a decent amount of steps, which is 25,000, and it is currently achieving 53% accuracy. With more training, the model's accuracy will improve, but we'll stop here for now. Now, after training the model, we need to save the model and load it for inferencing. So the model saving is similar to any PyTorch model saving and loading. So we have saved the model, and now we'll load the model for inferencing again. We'll use the native PyTorch methods to do everything here. So the model is loaded now. Now we'll use some random example from the validation dataset and try to predict the label and see if the model can predict correct labels for those examples. As you can see, this is an image of a frog and the model is predicting frog here. Now that we have tested the CFAR code, it's time to use the most powerful features of PyMarlin: scaling and logging. We will use a GPU virtual machine to go through the next set of instructions. Here we have converted the notebook to a .py file and using a YAML-based config parser to parse the hyperparameters. YAML parser comes inbuilt with PyMarlin. Now let's start. We'll start with copying the entire CFAR example to a GPU virtual machine. Here is my GPU virtual machine here. So we'll copy everything here to the virtual machine first. Okay, now we have the entire example in our GPU virtual machine. We will quickly see what this virtual machine configuration is. It contains 4 V100 GPUs. Now we'll start with installing PyMarlin. I've already installed PyMarlin, so I won't be doing that again. Now we'll run this code which trains the CFAR model using a single GPU, similar to what we did in the Colab notebook. As you can see, it has started training the model. Okay, I'll stop the training now. Next, we will use mixed precision training. It only involves this small additional command. As you can see, we were able to easily extend single process training and use the mixed precision training without any code change. The mixed precision training involves a trainer backend called single process AMP, which is visible here. Now that we have used mixed precision training and single process GPU training, it's time to scale the model training to multiple GPUs. We can use PyTorch's torch.distributed.launch tool to launch multiple processes and use the distributed data parallel trainer to train multiple multiple processes to train the model. So two processes have been launched now, and as you can see, the two processes are training the model simultaneously in a distributed data parallel manner. As we saw, it was very easy to scale from single process to mixed precision to multiple processes by just adding additional arguments. Now my model is trained completely and I'm achieving around 52% accuracy here. Now the next part is to see how well the model was trained, and for that PyMarlin comes inbuilt with the TensorBoard logger. We can launch TensorBoard by running this command, which fetches the TensorBoard logs from the logs directory. PyMarlin automatically populates the log directly with the TensorBoard logs. So TensorBoard is running on my virtual machine now, and I can tunnel to port 6006 in my local machine using this command. So now I'm tunneled to port 6006 to my virtual machine. And yeah, the logs from my virtual machine can now be visible in my local machine. As you can see, the model finished 101. So in total 2 epochs, and here is the loss function output. The loss is steadily declining and it will decline further if we train the model. So, yep, that's it. Thank you very much.